Electricity and magnetism are interrelated and are also interconvertible. Let us look at a few examples. In this setup, an electric current passing through a conductor produces a magnetic field, which can be observed through the deflection of a magnetic compass needle placed near the conductor. This proves that moving electric charges produce magnetic fields. Electric motors work on this principle. However, in this setup, we see that an electric current is induced in a closed coil when subjected to a changing magnetic field. The phenomenon in which an electric current is generated by varying magnetic fields is called electromagnetic induction. Electric generators work on this principle. We will now discuss and learn about 3 experiments by Faraday and Henry relating to electromagnetism. In the first experimental setup, a coil is connected to a galvanometer. When a bar magnet with its north pole facing the coil is moved towards or away from the coil, the galvanometer needle deflects to the right and left side of 0 reading respectively, showing the presence of a current in the coil. Now, let us see what happens if the south pole of the magnet faces the coil. The galvanometer needle deflects to the left side of 0 reading as the magnet approaches the coil and deflects to the right when the magnet moves away from the coil, showing the presence of a current in the coil. The galvanometer needle deflects only as long as the bar magnet is in motion. Once the bar magnet comes to rest, the galvanometer needle settles down at 0 reading, indicating that there is no current in the coil. From all these observations, we can conclude that whenever there is relative motion between a bar magnet and a coil, an electric current is induced in the coil. In the second experimental setup, there are 2 coils. Coil 1 connected to a galvanometer, coil 2 connected to a battery. Due to the steady current in coil 2, a steady magnetic field is set up around the coil 2, and this magnetic field is also linked to the coil 1. When coil 2 is kept stationary and coil 1 is moved towards coil 2, a current is induced in coil 1 and the galvanometer needle deflects to the left of 0. When coil 2 is kept stationary and coil 1 is moved away from coil 2, a current is induced in coil 1 and the galvanometer needle deflects to the right of 0. If we keep coil 1 stationary and move coil 2 towards coil 1, a current is induced in coil 1 and a deflection is observed in the galvanometer needle to the left of 0. Now, if we keep coil 1 stationary and move coil 2 away from coil 1, a current is induced in coil 1 and a deflection is observed in the galvanometer needle to the right of 0. From all these observations, we can conclude that whenever there is relative motion between a current-carrying coil and a closed coil in which a galvanometer is connected, a current is induced in the closed coil. In the third experiment, a tap key is provided in the coil 2 circuit. Here, we can observe the deflection of the galvanometer needle even when the 2 coils are stationary. This deflection is observed only at those instants when the tap key is either switched on or off. This happens because of the change in magnetic field during switching on and off. When a ferromagnetic material like an iron rod is placed coaxially along the two coils, the effect of the magnetic field linked to the coil 2 increases due to the nature of the ferromagnetic material, as it allows more number of magnetic lines of force to link within the area of the coil. Hence, the deflection of the galvanometer needle increases, indicating an increase in the induced current. When electricity is passed through a conductor, it displays a magnetic effect. This effect is responsible for the magic you just witnessed. In this lesson, you will learn about the magnetic effect of electricity. At the end of this lesson, you will be able to describe the magnetic effect of electricity. Apply Maxwell's right-hand grip rule and Maxwell's corkscrew rule to locate the direction of magnetic field lines due to current-carrying conductor. List the properties of a magnetic field and field lines around a straight conductor, a circular coil, and a solenoid carrying current. Analyze an electromagnet. Apply Fleming's left-hand rule to find out the direction of force on a current-carrying conductor in a magnetic field. And demonstrate the construction and working of an electric motor. Hans Christian Ørsted conducted an experiment to demonstrate that electricity produces a magnetic effect. The experiment is set up for you as you can see. Let's see what happens if we close the key to allow current to pass from south to north. The magnetic needle originally points north. However, when current passes through the wire from the south to the north, the needle deflects to the west. As you saw in Ørsted's experiment, when an electric current passes through a conductor, a magnetic field is created around the conductor. This phenomenon is called as the magnetic effect of electricity. Let's analyze this magnetic effect further. You will observe that if you place the compass above the wire and allow current to pass from the south to the north, the compass needle deflects to the east. If you reverse the direction of the current in the wire, the direction of the deflection of the magnetic needle is reversed. The angle of deflection is directly proportional to the strength of the current through the wire. A magnetic field is the extent of space surrounding a magnet where the magnet's effect can be felt. Thus, it represents the region under the influence of the magnet, just as an electric field represents the region of electric influence. A magnetic field consists of a number of magnetic field lines, generally referred to as magnetic lines of force. Magnetic field lines represent the lines of action of the force acting on a unit north pole placed in the magnetic field. magnetic field lines are closed continuous curves, never intersect each other, mutually repel each other, travel from the north to the south outside the magnet, and travel from the south to the north within the magnet. You can determine the direction of magnetic field lines due to a current-carrying conductor using Maxwell's right-hand grip rule. According to this rule, if you hold a conductor in your right hand with your fingers curled around it and your thumb stretched out as shown, then your thumb denotes the direction of the current in the conductor, and the direction of the curling of your fingers indicates the direction of the magnetic field lines due to the conductor. In the example shown, the current in the wire AB passes in the direction of the thumb, from end A to end B. The direction of the magnetic field due to the current in the wire is represented by the curl of the fingers, as shown. This rule is also called Maxwell's corkscrew rule. Consider a right-handed corkscrew kept parallel to a current-carrying conductor. On turning, if the screw advances in the direction of the current, then the direction of rotation of its head gives the direction of the magnetic field lines due to the conductor. Thus, magnetic field lines around a current-carrying conductor are in the form of concentric circles and can be either clockwise or counterclockwise depending on the direction of the current. Magnetic field lines vary with the shape and form of the conductor. Let's take a look at the magnetic field and field lines around a straight conductor, a circular loop, and a solenoid. An experiment will help you understand how magnetic field is spread around a straight current-carrying conductor. To begin the experiment, we fix a white sheet on a cardboard, which is clamped to a stand. Next, we pass a thick copper wire connected to a battery and key through a hole at the center of the cardboard. Finally, some iron filings are sprinkled on the board and current is allowed to pass through the wire by switching the key on. You will observe that when the current flows through the wire, the iron filings arrange themselves in a concentric circular pattern. By placing a magnetic compass on any circular field line represented by the iron filings, you can also detect the direction of the magnetic field lines. The direction of the compass needle indicates the direction of the magnetic field. Further, if you change the direction of the current in the wire, you will observe that the direction of the compass needle is reversed. Thus, based on this experiment, you can conclude that a magnetic field around a straight current-carrying conductor consists of concentric circular field lines. The direction of the magnetic field lines depends on the direction of the current in the conductor. In general, magnetic field lines around a straight current-carrying conductor form concentric circles around every point on the conductor, with the center on the axis of the conductor. Lie in a plane that is perpendicular to the length of the conductor. Increase or decrease with an increase or decrease in the strength of the current respectively. Create a cylindrical magnetic field around the conductor. We can analyze the magnetic field of a current-carrying circular loop through another experiment. We begin by fixing a white sheet on a cardboard and clamping it on a stand. Next, we pass a thick copper wire through two holes on the cardboard so that it makes a curve and forms the shape of a loop. Then, we connect the ends of the loop to a battery and a key. Finally, we sprinkle some iron filings on the board and allow current to pass through the loop. When current passes through the loop, the iron filings arrange themselves in two sets of concentric circles on the cardboard. Further, if you place two compasses on each set of concentric circles, you will notice that the needles point in opposite directions. This shows that the magnetic field due to a current-carrying circular loop takes the form of two oppositely directed sets of concentric circles. Magnetic field lines around a current-carrying circular loop have the following properties. The lines are circular near the loop and tend to get elliptical away from it. They travel in the same direction within the area enclosed by the loop. They are parallel to each other near the center of the loop, indicating the uniformity of the magnetic field. They lie in a plane perpendicular to the plane of the loop at its center. They increase or decrease with an increase or decrease in the strength of the current respectively. These lines create a south pole at the face of the loop where the field lines enter the loop and the current in the loop is in a clockwise direction. They create a north pole at the opposite face of the loop where the field lines leave the loop and the current in the loop is in a counterclockwise direction. A solenoid consists of an insulated conducting wire wound on a cylindrical tube made of plastic or cardboard. Thus, a solenoid consists of a number of circular loops. That is, it constitutes a coil. The length of a solenoid is greater than its diameter. When current passes through a solenoid, each loop in the solenoid behaves like a tiny bar magnet, with the south pole of one loop facing the north pole of its adjacent loop, and vice versa. Thus, a solenoid consists of a number of tiny magnets of equal strength. All the tiny magnets in the solenoid together behave like a bar magnet. The end of the coil, at which the current in the coil is in a clockwise direction, develops south polarity, while the other end, where the current in the coil is in a counterclockwise direction, develops north polarity. To analyze the magnetic field and field lines due to a current-carrying solenoid, here is an experiment. In this experiment, we fix a solenoid in a slit in a cardboard. We connect this solenoid to a battery and a key. Finally, we sprinkle iron filings on the cardboard and close the key to complete the circuit. When current passes through the solenoid, the iron filings arrange themselves in a pattern that represents the magnetic field lines due to the solenoid. These lines can be traced using compass needles. Magnetic field lines due to a solenoid are parallel to each other and to the axis of the solenoid within it, travel from the south pole to the north pole within the magnet, and travel from the north pole to the south pole outside the magnet. The density of magnetic field lines indicates the intensity of a magnetic field measured in Newton per ampere meter or Tesla. The intensity of a magnetic field can be increased by increasing the strength of the current, increasing the number of turns in the solenoid, or inserting a soft iron core in the solenoid. Using electric current, you can create magnets out of metals like iron, nickel, and cobalt. Magnets created using electric current are called electromagnets. An electromagnet is a magnet made of a coil of insulated wire wound around a soft iron core. The iron core is magnetized when an electric current passes through the wire. In other words, an electromagnet is a solenoid with an iron core. Electromagnets are more useful than permanent bar magnet in the following ways. Electromagnets have a stronger magnetic field than permanent bar magnets. It is possible to reverse the polarity of electromagnets, but not in the case of permanent magnets. Electromagnets can be easily demagnetized by interrupting the current. However, it is difficult to demagnetize permanent magnets. In electromagnets, the intensity of the magnetic field can be easily varied. However, magnetic fields of permanent magnets are of fixed intensity. You can convert an electromagnet into a permanent magnet by using a steel core. A magnetic field exerts a force on the magnetic objects under its influence. Therefore, a current-carrying conductor kept in a uniform magnetic field experiences a force that tends to drive it away from the field. The direction of the force on a current-carrying conductor in a magnetic field can be determined using Fleming's left-hand rule. To understand this rule, stretch the forefinger, middle finger and the thumb of your left hand, holding them at right angles to each other. If the forefinger gives the direction of the external magnetic field and the middle finger points in the direction of the current in the conductor, then the thumb gives the direction of the force on the conductor. An electric motor converts electrical energy into mechanical energy using the magnetic effect of electricity. You find electric motors in household appliances such as fans, refrigerators, washing machines, pool pumps, and floor vacuums. An electric motor is built on the principle that a current-carrying coil rotates when kept in a strong magnetic field as it experiences torque. An electric motor consists of 6 main parts. An armature that consists of laminated sheets of soft iron, through which passes a shaft. A coil, in the form of an insulated copper wire looped over the armature. A magnet that produces a strong and uniform magnetic field. A commutator, which is a metal ring split into two and is also referred to as split rings. This commutator is connected to the two ends of the coil. The shaft passes through the center of the commutator. 2 carbon brushes tightly fixed to the 2 split rings connecting them electrically to the coil. A battery that provides electrical energy to the motor. Let's examine how an electric motor works. Consider a rectangular coil PQRS placed horizontally between the north and south poles of a magnet and connected to a battery. The end of PQ part of the coil is connected to the battery through the split ring S1 and the brush B1. The end of RS part of the coil is connected to the battery through the split ring S2 and the brush B2. Initially, current is directed from P to Q in the arm PQ and from R to S in the arm RS. This arrangement is similar to that of a current-carrying conductor in a magnetic field. According to Fleming's left-hand rule, the force on PQ acts in an upward direction and on RS in a downward direction, forming a couple. The coil begins to rotate until its plane becomes vertical, that is, perpendicular to the direction of the magnetic field. Magnetic fields of the coil and the magnets become parallel to each other as the coil rotates by 90 degrees and the couple acting on the coil becomes 0. However, the coil rotates further through 180 degrees due to inertia. The plane of the coil becomes horizontal again. When the coil rotates by 180 degrees, the split rings also rotate along with the coil. Now, the split ring S1 connects end PQ of the coil to carbon brush B2. Similarly, S2 connects RS to B1. This reverses the current through the coil. The current now enters the coil through S2, passes along S, R, Q, P, and leaves the coil through S1. The torque acting on the coil causes PQ to go down and RS to go up. The torque acts on the coil until it rotates through 90 degrees. Further, it rotates through another 90 degrees due to inertia and becomes horizontal again. On completing one full rotation, the split ring S1 connects PQ once again to carbon brush B1. Similarly, S2 connects RS to B2. Thus, as long as the coil is connected to a battery, it continues to rotate and convert electrical energy into mechanical energy. The power of an electric motor depends on the strength of the current through the coil, the number of turns in the coil, the area of cross-section of the coil, the strength of the magnetic field, and the lamination of the iron core. This lamination reduces energy losses.
Look, the can is falling off. What do you think is wrong? Can you fix it for me?
I don't think there is anything wrong with the toy. It's probably the battery.
But I thought it's a magnet the toy crane uses to attract metal objects. What does the battery have to do with the magnet?
The magnetic effect that the toy uses is actually created by electricity. The tip of the string of your toy crane contains an electromagnet.
What do you think James is talking about? What does electricity have to do with magnetic properties? Let's find out. In this lesson, you will learn about the magnetic effect of electric current, the electromagnet and its applications such as an electric bell. At the end of this lesson, you will be able to explain the magnetic effect of electric current, describe an electromagnet, and demonstrate how an electromagnet is used in an electric bell and certain other applications.
When an electric current is passed through a wire wound around an iron bar, the bar behaves like a magnet. This magnet is now called an electromagnet. An electromagnet is formed due to the magnetic effect of electric current.
This is like the one in my toy crane.
Right, till the battery supplied electric current to the iron bar at the tip of the string of your toy. The iron bar worked as a magnet. When the battery ran out, there was no current, and hence the crane lost its magnetic properties. It will behave as a magnet once you replace the batteries.
It is kind of difficult to believe. Can you show me how this works?
Sure. I will conduct for you the experiment through which Hans Christian Ørsted discovered the magnetic effect of electricity. Hans Christian Ørsted was a Danish scientist. One evening, while preparing for a lecture, he noticed the deflection of the needle of a magnetic compass kept near a wire that was connected to a battery. The deflection occurred each time the battery was switched on and off. Let's carry out the experiment to see what the scientist observed. Let's take a circuit composed of a switch, a battery containing 2 cells, and a bulb. Make sure that the long conductor, which is the wire through which current flows, is along the north-south direction, and that initially the circuit is switched off. We now place a magnetic compass below the wire in the circuit. Initially, the north pole of the magnetic needle of the compass points towards the geographical north. Switch on the circuit and simultaneously observe the compass.
Hey, the compass needle has deflected and points in a different direction.
Right. This is exactly what scientist Hans Christian Ørsted noticed. Now, we'll switch off the circuit. See what happens to the needle now.
It has come back to its original position.
Yes, that is the north-south direction. So, what does that tell you?
Obviously, a magnetic field is getting created.
Right. Hans discovered that the deflections were due to the magnetic field being created by the current-carrying wire.
That's a cool experiment.
If the direction of the current is reversed by reversing the connections of the battery, the direction of the deflection of the compass needle is also reversed. That is, if the current in the wire is along north to south, the deflection of the needle below the wire is towards the east. If the current flows from south to north, then the needle will deflect towards the west.
You showed me the magnetic effect of electricity. But in that experiment, we didn't really create an electromagnet, did we?
Well, no. To create an electromagnet, we need some additional components. Come, I'll show you how to create an electromagnet. We will need 2 pieces of insulated copper wire, a nail, a battery containing 2 cells, a bulb with a holder, and some paper clips made of iron.
Here they are. But why do we need a bulb for making an electromagnet?
Good question. The bulb in the circuit provides resistance to the current. This prevents quick discharge of the battery that is being used. It basically prolongs battery life. Now, let's see. Let's wind 1 copper wire around the nail in one direction. Make sure that the wire does not overlap. We'll need to remove the plastic coating of the wire at both its ends, sufficient to connect to the battery. Now, we'll connect one end of this wire to the battery and the other end to one terminal of the bulb holder.
What about the other wire? Should we connect it to the other terminal of the battery?
That's right. We connect the ends of the other wire to the remaining terminal of the bulb holder and the other terminal of the battery. We are done. Now, let's place the paper clips near the nail.
Hey, the clips are clinging to the nail.
Yes, that's because the nail is now an electromagnet. When we disconnect the battery, the nail is no more an electromagnet. This is the principle used in the construction of an electromagnet. Very strong electromagnets can be made, which could be used for carrying heavy loads.
Yes, I remember studying about cranes with strong magnets attached to them in the earlier classes.
Yes, you're right. Such cranes are used for lifting material and for separating iron from scrap in industries. They're also used in medicine and in toys. So, what does that tell you? Every time an electric current is passed through a wire, a magnetic field is created around the current-carrying wire. Clearly, electric current has a magnetic effect, right?
Right. Electromagnets also help pick up cars to be put in the dumps, don't they?
Good observation. One of the common uses of the electromagnet is in the electric bell.
An electric bell?
Yes, there is an electromagnet in it.
That sounds interesting.
Come, let me show you how it works. First, let's see the parts of the electric bell before getting to know how exactly it works. An electric bell primarily consists of an iron core on which is wound a wire as a coil. One end of the coil is connected to one terminal of a battery. The other end of the coil is connected to a steel rod that acts like a spring to the hammer touching the screw contact. The other terminal of the battery is connected to the screw contact with a switch in the middle. Now, let's see how an electric bell works. When the switch is on, electric current flows through the coil and the iron core acts as an electromagnet. This iron core, which is now an electromagnet, attracts the hammer towards it. The hammer hits the bell and produces a sound. When the hammer moves towards the iron core, the circuit breaks at the screw contact. At this point, the iron core ceases to be an electromagnet. The spring action of the steel rod pulls the hammer back to its original position and then touches the contact screw again to complete the circuit. Current flows through the coil again and the hammer strikes the bell again. This process continues over and over again till the time the switch is on, producing a ringing sound. There are applications of electromagnets other than the electric bell, toys, and in iron industries. Electromagnets are used in transformers that transmit electricity from one place to another, and also in electromagnetic trains, called maglevs.
This brings us to the end of this lesson on electromagnet and its effect. In this lesson, you have learned to explain the magnetic effect of electric current, describe an electromagnet, and demonstrate how an electromagnet is used in an electric bell and in certain other applications. You know that a current-carrying conductor produces a magnetic field around it. If this conductor is placed in a uniform external magnetic field, such that the two magnetic fields are not oriented in the same direction, then the magnetic fields interact with each other. This interaction causes a force on the conductor. Thus, a current-carrying conductor placed in an external uniform magnetic field in a direction other than the direction of the magnetic field will experience a force. This can be demonstrated by an experiment. The experiment set up here shows a conductor AC which is free to move in a magnetic field of strength B between the poles of a magnet. The length of the conductor is normal to the direction of the magnetic field. The ends A and C of the conductor are connected to a rheostat, key, and a battery in series. It is experimentally observed that when no current passes through the conductor, no force acts on the conductor, and it does not move. When the key is pressed and current passes through the conductor, a force F acts on the conductor in a direction perpendicular to the plane containing the direction of the current and the magnetic field. Due to this force, the conductor begins to move in the direction of the force. When the direction of the current through the conductor is reversed, the direction of its motion is also reversed, indicating a reversal in the direction of the force. Also, on reversing the direction of the magnetic field, the direction of motion of the conductor is reversed, indicating a reversal in the direction of the force. When the conductor is placed such that the current in it is parallel to the direction of the magnetic field, it does not move, indicating that the force on it is zero. Experimentally, it is found that the magnitude of force F acting on a current-carrying conductor placed in a uniform external magnetic field is directly proportional to the strength of the current I through the conductor, the strength of the uniform magnetic field B, the length of the conductor L, sine of theta, where theta is the angle between the direction of the magnetic field and the direction of the current through the conductor. Combining all these expressions, we get F is proportional to the product of BIL sine theta. Replacing the proportionality symbol with a constant K, we get force F is equal to K into BIL sine theta. The unit for the strength of a magnetic field is chosen such that the value of K is equal to 1. Then the expression becomes F is equal to BIL sine theta. Let this be equation 1. Any change in the value of the angle affects the magnitude of the force on the current-carrying conductor placed in the uniform external magnetic field. When the current-carrying conductor is placed parallel to the direction of the magnetic field, theta is equal to 0 degree or 180 degree. If the current through the conductor is in the direction of the magnetic field, then theta is 0 degree. If the current through the conductor is in a direction opposite to that of the magnetic field, then theta is 180 degree. The value of sine 0 and sine 180 is 0. And hence, the force F is equal to 0. When the angle between the direction of the current through the conductor and the magnetic field is 45 degree, the value of sine 45 is 1 by square root of 2. And hence, force F is equal to BIL by square root of 2. When the current passing through the conductor is perpendicular to the direction of the magnetic field, theta is equal to 90 degree. The value of sine 90 is 1. And hence, force F is equal to BIL. Let this be equation 2. This is the maximum force exerted on a conductor of given length with constant current and strength of the external magnetic field. From this expression, we can derive the unit for magnetic field strength. Rearranging the terms in the expression for B, we get B is equal to F by IL. The SI unit of force is Newton. The unit of current is ampere and the unit of length is meter. Hence, the SI unit of magnetic field strength is Newton per ampere meter. Sometimes B is also expressed in terms of Weber per meter square. Hence, 1 Weber per meter square is equal to 1 Newton per ampere meter. Weber per meter square is also referred to as Tesla, named after Nikola Tesla, the Serbian-American inventor, electrical engineer and scientist. You know that the conventional electric current through a conductor is due to the flow of positive charges through it. Actually, it is the flow of free electrons in the conductor that constitutes electric current. You just saw that a current-carrying conductor placed in an external uniform magnetic field experiences force. This implies that the moving electrons through the conductor also experience some force. Therefore, whenever a charge is moving at an angle theta with the external magnetic field, it experiences a force, but only when theta is other than 0 degrees or 180 degrees. This force is called the Lorentz Force, named after the Dutch physicist Hendrik Antoon Lorentz, who derived the expression for it. Consider a positive charge of magnitude q moving with uniform velocity v for a time t in a magnetic field of strength B. The current due to the motion of the charge I is given by q by t. If L is the distance covered by the charge in time t, then the velocity v of the charge is given by L by t. From this expression, we get T is equal to L by V. Substituting the expression for time in the expression for current and simplifying, we get the expression for current as I is equal to QV by L. Let this be equation 3. To get the expression for the magnitude of the force on the moving charge in an external uniform magnetic field, we substitute the expression for current from equation 3 in equation 1 and simplify. We get F is equal to BQV sin theta. Let this be equation 4. Here, theta is the angle between the direction of motion of the charge and the direction of the magnetic field. If the charge moves in the direction of the magnetic field, then theta is equal to 0. As sine of 0 is 0, we have the force on the moving charge to be 0. For a given value of the charge, moving with a constant velocity in a magnetic field of given strength, to have the maximum magnitude of the force, we need to have the highest value of sine theta. The value of sine theta is the highest when theta is 90 degrees. Hence, the magnitude of the force on the charge is maximum when it moves normal to the direction of the magnetic field and is given by F is equal to BQV. The direction of the Lorentz force is given by Fleming's left-hand rule. According to the rule, if you stretch the forefinger, middle finger, and thumb of your left hand such that they are mutually perpendicular to each other, and if the forefinger indicates the direction of the magnetic field and the middle finger the direction of motion of the positive charge, then the thumb indicates the direction of force on the charge. The same rule applies to a current-carrying conductor, except that the middle finger indicates the direction of current in the conductor. Here, the thumb indicates the direction of the force on the conductor. There is no potential difference between the ends of this coil of wire. How then does the bulb glow? A magnetic field gives rise to an electric current in a conductor due to electromagnetic induction. In this lesson, you will learn how electric current is induced due to a magnetic field. At the end of this lesson, you will be able to explain electromagnetic induction through Faraday's experiment, state Faraday's law of electromagnetic induction, use Faraday's law combined with Lenz's law to find the direction of a current, apply Fleming's right-hand rule to identify the direction of an induced current, demonstrate the working of electric generators and explain domestic circuits. You just observed that there was no electric cell to maintain a potential difference across the circuit. Yet, the bulb started glowing. When the wire is moved across a magnetic field, the free electrons in the wire experience a force that makes them move through the wire, inducing an electromotive force EMF, and thus an electric current in the wire. This process of generating an EMF in a conductor by moving the conductor through an external magnetic field is known as electromagnetic induction. When a conductor is moved in a magnetic field or kept in a fluctuating magnetic field, the magnetic flux linked with the conductor changes. This change in magnetic flux induces an EMF across the conductor. The EMF generated in this way is called an induced EMF, and the resulting current is called an induced current. The phenomenon of electromagnetic induction was first studied by Michael Faraday. Michael Faraday hypothesized that current induced in a coil is due to a changing magnetic field. To test this hypothesis, he conducted an experiment. You can observe this experiment to verify Faraday's law. To conduct Faraday's experiment, we will begin by winding an insulated wire over a hollow paper cylinder to make a coil. Next, we connect a galvanometer to the coil. Finally, we insert a powerful bar magnet in the cylinder with its south pole entering the coil first. We observe that when the magnet is moved in, the galvanometer needle deflects towards the left. When the magnet is moved out of the coil, the galvanometer needle deflects towards the right. If the magnet is not moved inside or outside the coil, meaning the magnet is stationary, the needle immediately returns to zero. The deflection of the needle when the magnet is moved in or out indicates that a current has been induced in the coil. Thus, an EMF is induced in the coil due to the movement of the magnet. Faraday's experiment confirmed that a moving magnetic field is necessary for electromagnetic induction. The direction of deflection of the galvanometer needle depends on which pole is inserted in the coil first. For example, in the experiment you saw, if the magnet is inserted with north pole first, the needle will deflect in the opposite direction as that of the previous case. In Faraday's experiment, you observed that a relative change in a magnetic field induces EMF in a conductor. The magnetic field can be changed in two ways: by relative motion between the coil and the magnet, as you saw in Faraday's experiment, or by winding two coils on the cylinder near each other, as shown. In the second case, one coil is connected to a battery with a key. This coil is called the primary coil. The other coil is connected to a galvanometer and is known as the secondary coil. When the key is pressed, a current passes through the primary coil. This current produces a magnetic field. As the magnetic field around the primary coil increases, the magnetic field associated with the secondary coil increases equally. The change in the magnetic field associated with the secondary coil induces EMF in the secondary coil. This EMF can be observed through the deflection of the needle in the galvanometer. The quantum and direction of EMF induced due to electromagnetic induction depends on 5 factors. Let's examine these factors one by one. The first factor is the direction of motion of the magnet in a coil. This determines the direction of the induced current. If you insert the magnet in the coil, the galvanometer needle deflects in a particular direction. When you move the magnet out, the needle deflects in the reverse direction. Thus, the direction of current gets reversed when the direction of motion of the magnet changes. The direction of the induced current in the coil also depends on the orientation of the magnet. If you move the magnet into the coil with its north pole first, rather than the south pole first, the direction of the induced current in the coil is reversed. The speed of motion of the magnet through a coil determines the strength of the induced current. Thus, if you increase the speed of the motion of the magnet, the EMF generated increases, and vice versa. The strength of the magnet is another important factor. The quantum of EMF induced in a coil is proportional to the strength of the magnet. The stronger the magnet, the higher the induced EMF, and thus increased induced current in the coil. Finally, the number of turns in the coil also affects the induced EMF. Using a coil with a greater number of turns increases the induced EMF. Based on his experiments, Faraday postulated a law on electromagnetic induction. Faraday's law states that the induced electromotive force E in any closed circuit is directly proportional to the rate of change of the magnetic flux through the circuit. You can determine the direction of the current induced when a conductor moves in a magnetic field using Fleming's right-hand rule. This rule is also known as the generator rule. To use Fleming's right-hand rule, stretch the thumb, the index finger and the middle finger of your right hand so that they are at right angles to each other as shown. If the index finger points in the direction of the magnetic field and the thumb indicates the direction of the motion of the conductor, then the middle finger indicates the direction of the induced current in the conductor. Consider a conductor AB connected to a galvanometer placed in a magnetic field. The direction of the magnetic field is from the North Pole to the South Pole. When you move the conductor up, the galvanometer needle deflects to the right. This rightward deflection indicates the direction of the current in the conductor from end A to end B. If you move the conductor downwards in the magnetic field, the galvanometer needle deflects to the left. This indicates the direction of the current in the conductor from B to A. Thus, you can see that the direction of the magnetic field, the movement of the conductor, and the induced current are at right angles to each other. Electric generators are based on the principle of electromagnetic induction. Generators are used to generate electricity in power plants for transmission and distribution of electricity over power lines, and to produce electric power required for aircrafts, ships, and trains. Dynamos used in automobiles are similar to generators, but they produce relatively less power. There are two types of electric generators: AC generators and DC generators. An AC generator is made up of four major components: an armature consisting of a laminated soft iron core with copper windings with a large number of turns, two slip rings made of gunmetal, which are connected to the two ends of a coil and rotate with it, brushes to provide electrical contact between the external load and slip rings, and a powerful horseshoe magnet or an electromagnet. Now let's examine how a generator works. The rotation of an armature, PQRS, between the magnetic poles results in a change in the magnetic flux linked to the coil. This induces a current through the armature. Here is a step-by-step account of how the current is induced. Initially, the coil is vertical with PQ on top and RS at the bottom. This coil is rotated clockwise so that PQ goes down. As the coil rotates through 90 degrees, it becomes horizontal. At this stage, the change in flux with respect to the initial position is maximum. Hence, the current rises from 0 to maximum. The direction of current through each arm can be found using Fleming's right-hand rule. The current flows from brush B1 to brush B2. On rotating further by 90 degrees, the coil becomes vertical again. But now PQ is at the bottom and RS is at the top. The change in flux with respect to the initial position is 0. Hence, the current falls from its maximum in the same direction and becomes 0. Rotating the coil by another 90 degrees causes the current to increase in the opposite direction. Now the coil has rotated through 270 degrees from its initial position. Now the current flows from B2 to B1. On turning further by 90 degrees, the coil completes one rotation of 360 degrees. The change in flux with respect to the initial position is 0 at this point. Hence, the current falls in the same direction and becomes 0. Thus, the current rises and falls for every 180 degrees of rotation of the coil in opposite directions alternately. The faster the coil turns, the greater the frequency of the current produced by the generator. In an AC generator, the induced current changes its direction periodically and is therefore called alternating current. An AC voltage is continually changing between positive and negative. The rate of change in the direction of the current is called the frequency of the alternating current. It is measured in Hertz, that is, the number of cycles per second. The increase in value from 0 to the positive maximum, then the decrease back to 0, then the further increase to the negative maximum, and the decrease back to 0 is counted as one complete cycle. Like an AC generator, a DC generator also works on the principle of electromagnetic induction. However, a DC generator produces direct current and is commonly used in small-scale power generation devices such as a dynamo. A DC generator is equipped with a commutator, which is a pair of split rings, in a position similar to that of slip rings in an AC generator. A commutator helps in keeping the polarity of the brushes the same to ensure unidirectional current. The other major components of a DC generator are similar to that in an AC generator. A DC generator that contains a loop generates a pulsating DC current. To produce a more stable output, a coil with more turns is typically used. In a DC generator, when the coil rotates through 90 degrees, the change in magnetic flux induces an electromotive force of maximum strength. This current flows through the split rings to the brushes. When the coil is rotated further, at 180 degrees, the electromotive force becomes 0. At this point, the contact between the commutator and the brushes is reversed. The first brush now comes into contact with the second segment, while the other brush comes into contact with the first segment of the commutator. This keeps the current going in one direction. Most of the power plants in the world produce high-frequency alternating current that is supplied to industrial and household consumers through power grids. Electrical components and wires fitted in a household to supply electricity to various appliances form a domestic electric circuit. Let's see how electricity is distributed through domestic electric circuits. A network of overhead or underground cables brings power to our homes. Domestic electric circuits are connected to this network through main supply cables, commonly known as mains. The main supply cable has two wires. The first wire, usually in a red insulation cover, is called a live or positive wire. The second wire, insulated in black, is called a neutral or negative wire. Electric current enters a domestic electric circuit through the live wire. The neutral wire provides the return path for the current out of the circuit. These wires pass through the main fuse in a meter board. A main switch connects these wires to the line wires in the house. Line wires supply electricity to all circuits within the household. Separate circuits may be used for power lines supplying 15 ampere and 5 ampere current. This is to provide for varied current requirements of appliances. Appliances with higher power ratings, such as air coolers and geysers, require a 15 ampere supply. On the other hand, electrical fittings such as bulbs and fans run on 5 ampere supply. Domestic electric circuits also have earth wires used as a safety measure against any leakage of current. In case of power leakage, appliances with metallic bodies such as electric irons and water geysers may convey excess current to a human body in contact. This can result in an electric shock and may, at times, also prove fatal. Connecting the metallic bodies of these appliances to earth wire ensures that any current leakages are conveyed to the earth. Hence, earth wires save users from severe electric shocks. Earth wires are generally insulated in green color. An electric fuse is an important component of all domestic circuits. An electric fuse is a safety device used to protect an electric circuit against excessive current. If your electrical appliances receive very strong current, they could get damaged and stop functioning. To prevent damage from fluctuations in the current, an electric fuse is used in the domestic circuits. You know that electromagnetic induction is the phenomenon in which an electromotive force and electric current, due to it, is induced in a coil whenever there is a change in the magnetic flux associated with the loop. You also know that the magnitude of the induced electromotive force is directly proportional to the rate of change of magnetic flux associated with the coil. The magnitude of the induced EMF also depends on the number of turns in the coil and the area of its cross-section. The direction of the induced EMF is given by two rules: Fleming's right-hand rule and Lenz's law. In this module, we discuss Lenz's law. According to Lenz's law, in all cases of electromagnetic induction, the direction of the induced current is such that it opposes the cause that produces it. Let us understand Lenz's law through an activity. Consider a closed circular coil with a certain number of turns. Say N. The terminals of the coil are connected to a galvanometer at rest, as shown here. The galvanometer shows zero deflection. We take a bar magnet and place it such that the axis of the magnet is along the axis of the coil, and the north pole faces the coil. You know that the magnetic field lines associated with the bar magnet come out of the magnet at its north pole and enter at its south pole. Now we move the magnet towards the coil. As we move the magnet towards the coil, the magnetic field lines also approach the coil. Thus, the magnetic field associated with the magnet increases. This induces an EMF in the coil, and an induced current passes through it. According to Lenz's law, the direction of the induced current is such that it opposes the cause that produces it. This implies that the current should oppose the north pole of the bar magnet. Let us find out how this happens. We know that a current-carrying conductor produces a magnetic field around it. If the conductor is in the form of a coil, and if the current in the coil is in the clockwise direction as seen from your side, then a magnetic south pole is formed on the plane of the coil facing you. On the other hand, If the current in the coil is in the anti-clockwise direction, as seen from your side, then a magnetic north pole is formed. Now, in the context of moving the bar magnet towards the coil, with the north pole of the magnet facing the coil, the magnet should be repelled according to Lenz's law. Hence, a magnetic north pole should be formed on the plane of the coil facing the bar magnet. This implies that the induced current in the coil, as seen from the bar magnet, is in the anti-clockwise direction. This can be observed from the deflection of the needle in the galvanometer. Let us term this as case 1. Now, if the bar magnet is moved away from the coil, then the induced current in the coil should oppose the motion of the magnet. This happens when a south pole is formed on the plane of the coil facing the bar magnet. Thus, the induced current in the coil should be in the clockwise direction as observed from the magnet. This can also be observed by the deflection in the galvanometer needle in a direction opposite to that observed in case 1. Let us term this as case 2. The bar magnet is now reversed so that the south pole faces the coil. When the bar magnet is moved towards the coil, now the induced current in the coil is in the clockwise direction so as to oppose the motion of the magnet towards it. In this case, a magnetic south pole is formed on the plane of the coil facing the bar magnet. Let us term this as case 3. Here, we observe that the direction of deflection in the galvanometer is the same as in case 2. On the other hand, when the bar magnet is moved away from the coil, the induced current in it is in the anti-clockwise direction as observed from the magnet. In this case, a north pole is formed on the plane of the coil facing the magnet. Let this be case 4. Here, we observe that the deflection of the galvanometer needle is the same as observed in case 1. Another important thing to note in Lenz's law is that it complies with the law of conservation of energy. Let us find out how. When the bar magnet is brought near the coil, the number of magnetic field lines linked with the coil increases, producing an induced EMF. According to Lenz's law, the direction of the induced EMF is to oppose the motion of the magnet. Hence, work has to be done against it to move the magnet further. This work is converted into electrical energy. On the contrary, if the direction of the induced EMF were to help the motion of the magnet, then the magnet would begin to move faster, producing electrical energy. In other words, electrical energy would be produced without doing any external work, which is impossible according to the law of conservation of energy. Hence, the induced current in the coil passes in a direction so as to oppose the motion of the magnet. Thus, Lenz's law is in compliance with the law of conservation of energy. A transformer is a device used to increase or decrease the voltage of an alternating current. It is used in power transmission to reduce power losses and to increase the efficiency of power supply. A transformer changes voltage, but not the frequency of the alternating current. There are two types of transformers. They are step-up transformer and step-down transformer. A step-up transformer is used to increase a low-voltage alternating EMF to a high-voltage alternating EMF. A step-down transformer is used to decrease a high-voltage alternating EMF to a low-voltage alternating EMF. Transformers work on the principle of mutual induction. According to the principle of mutual induction, when two coils are placed close to each other, and if one of them carries a time-varying current, then a current is induced in the other coil. A transformer consists of a laminated core made from thin rectangular frames of soft iron. The frames are placed one over another and insulated from each other by lacquer, a kind of varnish. On one arm of the core, a coil P of insulated copper wire is wound. This coil is called the primary coil and is connected to an alternating voltage source, whose voltage is to be stepped up or stepped down. Let the number of turns in the primary coil be Np. On the other arm, another coil S of insulated copper wire is wound. This is the secondary coil. The induced alternating EMF is obtained as an output from the terminals of this coil. Let the number of turns in the secondary coil be Ns. The ratio Ns to Np is called the turns ratio or transformer ratio. When the terminals of the primary coil are connected to a source of alternating EMF, an alternating current through the primary coil produces varying magnetic field through the core. Thus, the magnetic flux through the core varies with time. Magnetic flux phi is a measure of the quantity of magnetism, being the total number of magnetic field lines passing through a specified area in a magnetic field. The advantage of using a closed core in the transformer is that it gives a closed path for the magnetic field lines. As a result, almost all the field lines produced by the current through the primary coil are linked with the secondary coil. This avoids leakage of magnetic flux and increases the efficiency of the transformer. According to Faraday's law, the magnitude of the induced EMF, E, is directly proportional to the rate of change of magnetic flux linked with the coil, d phi by dt. The EMF in the primary coil, EP, is equal to minus Np into d phi by dt, where d phi by dt is the rate of change of magnetic flux linked with the primary coil. The minus sign is in accordance with Lenz's law. Let this be equation 1. For an ideal transformer, the primary coil has zero or negligible resistance. Therefore, induced EMF, EP, is equal to voltage across the primary coil, Vp. Let this be equation 2. From equations 1 and 2, we get Vp is equal to minus Np into d phi by dt. Let this be equation 3. The magnetic flux linked with the secondary coil is the same as that of the primary coil. Because of the changing magnetic flux, we get induced EMF in the secondary coil, ES, equal to minus NS into d phi by dt. Let this be equation 4. As the transformer is considered an ideal one, we get ES is equal to Vs, which is the voltage across the terminals of the secondary coil. Let this be equation 5. From equations 4 and 5, we get Vs is equal to minus Ns into d phi by dt. Let this be equation 6. Dividing equation 6 by 3 and simplifying, we get Vs by Vp is equal to Ns by Np. Let this be equation 7. Thus, we observe that the ratio of the voltage across the secondary coil to that of the voltage across the primary coil of a transformer is the same as the ratio of the number of turns in the secondary coil to that in the primary coil respectively. For an ideal transformer, there is no power loss. Hence, the output power PO is equal to the input power PI. Electrical power is given by P equal to V into I, where I is the current. Let IP and IS be the current through the primary and secondary coils respectively. Thus, we have input power PI is equal to Vp into IP. Let this be equation 8. Similarly, output power PO is equal to Vs into Is. Let this be equation 9. Thus, we have Vs into Is is equal to Vp into Ip. Simplifying the expression, we have Vs by Vp is equal to Ip by Is. Let this be equation 10. From equations 7 and 10, we can relate the voltage, current, and turns ratio for an ideal transformer as the ratio of output voltage to input voltage is equal to the ratio of input current to output current, which is equal to the ratio of number of turns in the secondary coil to that in the primary coil. If the secondary coil has a greater number of turns than the primary, then the voltage gets stepped up. That is, the output voltage is higher than the input voltage. This type of a transformer is called a step-up transformer. In this type of a transformer, there is less current in the secondary coil than in the primary coil. For example, if the primary coil of a transformer has 100 turns and the secondary has 200 turns, then Ns by Np is equal to 2 and Np by Ns is equal to half. Thus, an input voltage of 220 volt Vp at input current Ip of 10 amperes gives an output voltage Vs of 440 volt. In other words, it is stepped up to 440 volt output at a current Is equal to 5 ampere. Conversely, if the secondary coil has less turns than in the primary coil, the transformer is called a step-down transformer. In such a case, the output voltage is less than the input voltage. That is, the voltage is stepped down or reduced, and the current increases. For example, if the primary coil of a transformer has 200 turns and the secondary has 100 turns, then Ns by Np is equal to half and Np by Ns is equal to 2. Thus, a 220 volt input voltage Vp at input current Ip of 10 ampere gives an output voltage Vs of 110 volt. That is, a step down to 110 volt output at current Is is equal to 20 ampere. Note that these equations apply only to ideal transformers in which there are no energy losses. However, in reality, all transformers incur small energy losses due to various factors, such as heat in the coils, eddy currents in the core, hysteresis loss in the core, magnetic field link loss. When current passes through the primary and secondary coils, it encounters resistance, because of which heat is generated. This heat is lost to the surroundings. To reduce the loss of energy in the form of heat, the wire used for the primary coil in a step-up transformer is thicker than that for the secondary coil. On the other hand, in a step-down transformer, the wire used for the primary coil is thinner than that for the secondary coil. When a varying current passes through the primary coil, the magnetic flux through the soft iron core changes, which induces circulating currents called eddy currents in the core of the transformer. The eddy currents produce heat. This can be reduced by laminating the core. A laminated core reduces eddy currents and the related energy loss. Due to the flow of alternating current through the primary coil, the core gets magnetized and demagnetized in quick succession. The energy loss associated with each cycle of magnetization and demagnetization is called hysteresis loss. This loss can be reduced by making the core out of soft iron. Soft iron is ferromagnetic in nature and has high magnetic permeability. It concentrates the magnetic field lines and reduces hysteresis loss. All the magnetic field lines due to the current in the primary coil do not get associated with the secondary coil. This is referred to as magnetic field link loss. This loss is reduced by taking a closed core. A transformer cannot be used with direct current since its working is based on changing magnetic flux produced by a time-varying current of a given frequency in one coil inducing a varying current of the same frequency in the other coil. Since the magnitude of direct current does not vary with time, a transformer cannot be used with direct current. A major use of transformers is in power transmission lines. Transformers are used in networks that transmit electricity over long distances. First, we use a step-up transformer to increase the voltage and consequently decrease the current in the transmission line. This reduces the loss of energy as heat. The voltage is then stepped down at various substations and utility poles before it reaches your home in the range of 220 to 240 volt. Typically, when electricity is transmitted at high voltages, the voltage is in multiples of 11. Thus, we have electricity being transmitted at 66, 33, 22 and 11 kilovolt. When electricity reaches your city from the generating stations, it is typically stepped down to 6.6, 3.3 or 1.1 kilovolt. At the substation in your area, it is stepped down to 440 volt for three-phase circuits and 220 to 240 volt for single-phase circuits. In India, domestic electricity supply is at 220 to 240 volt. But in the US, it is at 110 volt.